So in this course, we're going to look at the generalized finite element method for material interfaces. So we're going to start looking at this problem from a 1D point of view. So you see on your right, you have a bar. You know a bar element as from the advanced FEM class. We're all familiar with this type of structure already. It can take only an axial load, right? And there is a material discontinuity located at gamma, right? And then you have different material properties to the left and to the right. So in this case, you see that to the left you're going to have one Young's modulus, E1, and to the right, E2. And this mismatch in material properties is going to be responsible for discontinuity. In this case, a material interface, as we discussed earlier, is responsible for having a discontinuity in the gradient of a field. So this is what is called a weak discontinuity. Okay? In other words, if I try to plot the solution, the exact solution for that problem, which by the way is what type of polynomial. So if I have no body force there and I fix one end, so the displacement at the left end is going to be equal to 0, and then I just apply a force, a concentrated force at the right end, my solution is what order? My exact solution? 2? Linear. So if you plot that, you're going to get something that looks like this. Well, in this case, it's not linear, it's bilinear, right? Because of the discontinuity. So this here is the location gamma, and this is x, and this is u of x. Yeah? So as you can see, what happens here is that what we're going to say, the jump, so this symbol refers to the jump, the n. The n is basically a normal direction. Could be also dx in this context in 1D. But when we're talking about higher dimensions, then we really use the normal vector to the discontinuity. So this is basically, the way you define the jump is you take the derivative of that field and you evaluate that to the right, and then you do the same to the left. And then this is basically not equal to 0. Okay? So that's what it means. You have a jump in the gradient. So we use this as double square brackets to signify sometimes in papers the jump of a quantity. So if you take a look at the solution in the neighborhood of that element, so if let's say I want to look somewhere close here, let's say I just want to know how the solution can be represented there. So in the neighborhood of the discontinuity, I can actually represent my field as a sum of two different components. So I can say that my solution U, my displacement field, is going to be the sum of a solution that is that has a kink built in, and I use the hat for that, plus a solution that is actually smooth. So you can add these two parts together, right? Why not? Because then, if you think about the GFEM as a framework to paste together different types of approximations, or right, then you can think of, well, I can use GFEM to describe like the smooth part of the solution with some type of enrichment functions, and then the non-smooth part of the solution with a different type of enrichment functions. Right? So in this way, it gives you a lot of flexibility, because you can say, well, for the smooth part, then we can use something that we know is smooth. For example, what type of functions? Huh? Polynomials. That's what I would choose, definitely, to represent the smooth. And what about the non-smooth part? What can we use? Yeah, that's a very good, actually, that the Heaviside function is widely used in generalized finite element methods, but the Heaviside function is used to represent a discontinuity in the field itself, not in the gradient, okay? So there is a jump in the field itself if we use the Heaviside function here. So basically, this entire course is to see what are the types of enrichment functions that you can actually use. And well, for this particular problem where you have a weak discontinuity, there have been several enrichment functions proposed already in the literature, okay? So what we know about this decomposition is that if you take actually the jump of the smooth part, this is equal to what? Yeah, it's going to be equal to 0 because by definition there is no jump there. And again, just to write again what we wrote in the figure, this is going to be not equal to 0. And so now let's say if you now take the GFEM framework, and we're going to say, as we said the first class, that GFEM is a procedure to paste together different type of approximations. Remember that we talked about clouds, right, or supports. Who remember what a cloud or support was? If I give you a node X alpha, the support of X alpha was?
All of the elements which are connected to it.
Yes, all the elements that were connected to that node. That means, in other words, if that node X alpha, let's say, is a finite element node, that node is associated with a shake function that we called phi alpha. So basically, the support is where all those elements where that shake function is non-zero. That is another way to define what a cloud was. And now I want to write, if I want to make the HP extension of that, I'm going to say, well, I want to use the GFEM framework, and I want to represent my solution as pasting together local approximations. So look what I wrote here. Now, of course, I'm not dealing with a 1D problem anymore, because you can see that I'm already using the notation that we use for vectors. When I use a bar underneath, I'm basically referring to a vector. So I cannot bold characters here. But you see that equation is pretty much the GFEM approximation. What I'm doing here is I'm saying, well, I am taking the partition of unity of my mesh, which is defined by these shake functions phi sub alpha, right? And every single one of those shake functions is multiplied by a U function that reproduces some behavior in that particular cloud or support. That is what this equation is saying. Okay? So let's explain a bit more that concept. If you have a finite element mesh that has, let's say, 10 nodes, and you grab the first node, well, the first node is associated with the first shake function, that is phi1, right? Let's say that phi1 is in a corner in a two-dimensional domain, and that corner is connected to two triangular elements, for example. Yeah, that means that my support for that node 1, x1, is basically those two elements. Now, if I now take some function u tilde to represent some behavior that I want in that cloud, right? I can localize that behavior by multiplying that with the shake function phi1. Everyone is following me? Yeah? And why is this? Well, because we know already that these functions, these shake functions, have local support. So this phi1 is going to be non-zero only in what elements? Those two triangular elements that are connected to the node, right? That means that when I multiply a function, in this case the function is called u alpha tilde HP, right? When I multiply that function with that shape function, the behavior of that function u tilde is localized to those two elements alone. And this is in general terms what we do when we look at this type of formulation, this generalized finite element framework. You can see that as pasting together local approximations, because when I move to the next node, and I'm talking about now the second node x2, well, that node x2 is going to be connected to some triangular elements, and most likely the first triangular element that was connected to node 1 is also going to be connected to that node 2. But I can still multiply the shape function of node 2 with another function that represents some local behavior. Maybe the discontinuity now is passing through that cloud, right? And then I keep doing this, and I'm pasting together. I'm using the partition of unity to paste together local approximation in clouds. So that is basically a different way of thinking in terms of our approximation. Okay? Everybody with me there, right? Good. Yeah.
So for example, one element can be in two clouds, right? So you actually multiply the enriched function with both the shape functions.
You multiply the enriched.
You have one shape function, so you multiply the what's it?
You multiply. So if you take your first node is x1, let's just focus on the example that we were discussing. That first node has the shape function phi1, right? So I'm going to multiply some function by this shape function, okay? That is going to be non-zero in triangle x. Let's say triangle x is part of the first cloud. When I move to the second node, I take that shape function, right? And I multiply by some other function that is also going to be non-zero in that triangle x, right? That means that I am basically superposing the effect of the cloud 1 with the cloud 2, because the shape function phi1 is non-zero in triangle x, as well as the shape function phi2 is non-zero in triangle x. So you see that their effect is being superposed. That's why I'm saying that the way of seeing at this equation is that you're really pasting together approximations in clouds, right? That's the way you have to visualize this equation. So let me write a little bit what I just said. So this HP alpha defined on W alpha. Remember that W was the symbol that we decided to use for the clouds or supports. So phi alpha is the linear shape function and of course that whole sum has to be performed over the number of clouds or supports that you are considering in the approximation. So let me make a schematic so that we have a better picture of what we were talking about here. So say you have 1, 2, 3, 2, 3. Yeah. So this is my finite element mesh. We are talking about quadrangular elements, and say I have a discontinuity that runs through those elements. So I want to say, well, there is a material interface there, so I'm going to say on this side of the interface I have one Young modulus. On this side, I'm going to have another one. And I'm going to call some terminology here. I'm going to call all these elements representative elements. Okay? So these are going to be representative elements. Yeah? And all of these here I'm going to call them blending elements. So the ones that are called representative elements, the name is because, well, they are trying to reproduce some kinematics about the problem that we know, right? In this case, we have a discontinuity. And so if I want to reproduce that discontinuity, I have to do something particular in those elements. In the GFEM context, what I'm going to do is I'm going to add enrichments to the nodes of those, or all those finite elements that are cut by the discontinuity. Now, the blending elements are basically contiguous to the representative elements and are actually blending those representative elements with the rest of your mesh, which you know already is going to remain linear, so it's your standard finite element discretization. Okay, that's why they are called blending elements. And it is very interesting because some enrichment functions work very well, but some others do not work as well. And the main reason is because there are issues in blending elements. Yeah? So think about this idea of pasting together local approximations in the clouds. And now you take a look at the node that behaves or belongs simultaneously to a blending element and to a representative element, right? So you can immediately see that the shape function that is associated to that node, right? Somehow this node is enriched. That means that it's basically trying to reproduce some behavior in the representative element that has the discontinuity, but at the same time is connected to another cloud where there is no discontinuity. You understand this idea? That basically means that depending on the enrichment function that we use, there may be some issues in blending elements, right? So some enrichment functions are going to work, some enrichment functions are not going to work, or they are going to work, but our convergence rate is going to be reduced. Yeah?
Do we also have that same problem if the enrichment function would be 0 at that node, or then we
yeah.
in a let's say a 1D problem, do we still face the same problem?
What you want to be very careful with is that yeah, if the function is 0, it doesn't really matter. What is important is that the function, how the function behaves in the blending element, right? So your enrichment function can go to 0 at that node, but if it is non-zero in the blending element, then you may have issues. So it really depends on the choice of enrichment function to see whether you have issues in blending elements or not. Okay. In fact, there was a paper that was proposed to address this issue altogether by extending the area of enrichments and multiplying with an extra enrichment function, but that's another completely different story. I just want to get down some notation here. Remember that if we're looking at a node like this, right, and we called X alpha, basically, and I want to draw what would be the support of that, we're talking about all that stuff here. This is the support of W alpha. Yeah? Yeah. So now the objective is to reproduce that discontinuity, right? So what I want to do is, well, following the same idea of this pasting local approximations together, I want to represent my function as, we're going to rewrite this number of clouds, phi alpha of x. And now if you remember the equation that we wrote the first class for GFEM, then I'm going to have another sum U tilde alpha E times L alpha E. This is the way I'm going to represent my function. So now I'm basically expanding what these functions U look like. And I'm going to say, well, now I'm going to represent that function as a sum of enrichment functions multiplied by the corresponding enriched or generalized degrees of freedom. That's all I'm doing right now in this equation, in this step. Okay? So notice that even though I have the same terminology, let's say almost the same here and here, right? This one actually is my enriched degree of freedom. That you can also call generalized degree of freedom. Yeah? And this one here is my, what is it? Sorry? Yeah, that is my enrichment. For the local space. And well, this is just some mathematics. I call this Chi alpha, and this is non-zero only in the cloud, but don't worry about it. The idea is that the behavior of that enrichment function is basically localized to that cloud, and that is what is important here. So if you think of that cloud as just a set of interconnected elements to that node, and then I'm saying, well, I want in that cloud to be able to reproduce this discontinuity, right? So I'm going to do that by means of these enrichment functions, okay? Okay. By the way, you notice that so far we are dealing with the tilde part of the approximation, right? So we said initially that our approximation can be decomposed into two parts, one that is tilde and one that is hat, right? The tilde was the smooth part of the approximation, and that's what we have been developing now because I'm only dealing with tilde. So you can already ask yourselves, what type of enrichment functions are we going to use to reproduce the smooth part? And we had already an answer for that, which was, what was the answer to that question? To reproduce the smooth part of the approximation, we're going to use polynomials. Yeah? So since U HP is smooth, my L alpha I for the smooth part, so these are my enrichments. Who remembers the shape of these polynomial enrichments? We saw them the first class. X minus X alpha divided by H alpha. Remember this? Yeah? And then we have the same. Square. Yeah. Of course, we're dealing with vector, so this is X alpha and H alpha is the diameter. So if you remember, this is the way we define the enrichment functions for polynomials. We were actually shifting the polynomial so that it has a zero value at the location of the node. And we wanted to do that. This was very important to do this shifting. Why? Who remembers this? No one remembers. What was the reason why we decided to shift the polynomials so that they are exactly 0 at the location of the enriched node? No, the condition number is actually improved by the scaling by dividing by the diameter of the cloud. But what we said is that it was important to shift because then prescribing boundary conditions remains very simple, as in standard FEM, right? Yeah, that was the main reason we decided to do the shifting, right? The scaling took care of the condition part. Now the shifting was, to basically work with something that the enforcing Dirichlet boundary conditions was straightforward. Now, you remember all the discussion that we had in advanced FEM regarding the basis choice, right? That this was not really the best basis to choose. What was a better basis? Legendre polynomials. Okay. All right. Yeah, so then the smooth part of my solution can be written like this. Finally. And if you remember, when we actually had the product of a shake function and with the enrichment function, we call that, how did we call this? This product? Huh? Phi, yeah? In this case, it's tilde because it's representing the smooth part, alpha I of x, and this was our generalized shake function. Yeah? For the smooth part of U. So now we're good to go, at least for the smooth part. We're able to take, well, I want to say, I want to reproduce the smooth part of the solution by a third order polynomial. Well, I can have these enrichment functions and I can add them to my approximation, and I can now reproduce a third order polynomial for that part. And now we have to go to the non-smooth part. Yeah? So what are the enrichments that are used is a key question here. So how are we going to call this? Well, the non-smooth is the U hat, and we're going to call it HP. And keep in mind that I call this HP because, what I'm writing is basically the HP extension, right? So we are thinking about in terms of the combination of HFEM and PFEM, right? Whereby you can improve the accuracy by either reducing your mesh elements, size of the mesh elements, and then increasing at the same time the polynomial interpolation. Okay? That's why I call it HP. Right? So the size of the elements are going to take care of the H part of this approximation, and then by using generalized high order enrichment functions, that's going to take care of the P part of this interpolation. Okay? So for the smooth part, well, you would expect you have basically the same equation. So you have a loop, and then this is going to be now my approximation, my local approximation for the non-smooth part. that we can again expand the same way we just did it. And then let's just copy this whole thing. And I'm going to use now the sum equal to 1 to dl hat this time, because I'm going to use another type of enrichment functions. And this is now my generalized degrees of freedom for the non-smooth part. I'm going to move this stuff away. And then I have my enrichment functions that are going to be non-smooth. So again, this here represents the enriched DOF, and this guy here is my enrichment. And of course, we have to choose an appropriate enrichment function. So this function has to have a jump in the gradient, right? With jump. Okay? Yeah?
What you said about H and P. In this case, P, you said it's referring to the enrichment or not?
The P part, so I wrote UHP because I am thinking in creating an approximation that is used for the HP extension, right? So where you can reduce the error by different ways, right? In HP, you can reduce the error by making your element smaller, right? In which case you have the H part, and then the P part is by increasing the polynomial order, right? So that's why I wrote HP and not just H, as we would do, you know, that basically the interpolation is associated to a finite element discretization alone. No, it's the HP extension, so we can actually add polynomial enrichments to crank up the polynomial order. That's what I meant, okay?
It doesn't refer to what we learned in the first part or the first course, maybe that you apply, or you could apply the gender polynomials, I guess, as an enrichment.
Yeah, you could apply, if you change this basis here, and then you say, well, I'm going to use a different basis, like, for example, the gender polynomials, it still applies. So keep in mind that what we did in advanced FEM in the first course was we study how to reduce the approximation error, right? And we look at two different things. Basically reducing the size of our finite elements. This is the H version of finite element method. Or increasing the polynomial interpolation, right? When you combine these two, this is called the HP extension, right? When you combine these two into your solution, all right? You have a question?
Yeah, so the shift function by alpha here both
No. So far, right here, in what we're doing, we're dealing only with a partition of unity that is linear.
because just now you talked about that you wrote HP when the function was that.
Yeah, but the P part or the P extension part is basically tackled by this set of enrichment functions. But still, our partition of unity is linear. That does not mean that we cannot use a different partition of unity and say, well, let's work with quadratic shape functions as our partition of unity. That can also be done. But it is really not interesting because if I have a linear partition of unity and I want to really increase the polynomial interpolation order, I just keep adding polynomial enrichments. You see what I mean? Yeah? Okay. So now that we're ready to write the approximation of the whole thing. So by combining these two, let's say just for completeness, we're going to have my partition of unity, and that is going to paste together these two different things. Where we use one set of enrichment functions for the smooth part and a different set of enrichment functions for the other part. Okay? Let's take a look at how this works for a single element. So say you have one element, quadrangular element, and then your discontinuity goes through, and of course you have different material properties at each side. And now we said, well, for that particular element, my approximation is going to look like the sum between alpha equals 1 to 4. So I have 4 nodes, okay? Phi alpha, and those are my shake functions. And now I have the sum equals 1 to the dimension length of that smooth part of the enrichment. And then I call these, if you remember, these are my degrees of freedom, alpha I. And then I multiply by my smooth shake functions. And then I have the other component, the L hat. And I'm going to have U hat alpha I multiplied by L hat alpha I. So that in the notes, this example is not to be confused with the rest. Let's make something like that, okay? Now, I have a general expression for the field in that element. You see that I am basically, in that element, is intersected. How many clouds represent the behavior in that element? So if you look at it, I'm looking at the problem from the element point of view. But if we switch our thinking and we think about in terms of nodes and clouds, how many clouds are present there? 4. Yeah. So now let's think. What is the simplest case so that we develop from there? Remember that when you do computational work, you always start simple and then you build on top of that, right? You're adding more complexity as you move along. But what is the simplest case? So if I want to take my polynomial enrichments, what is the simplest thing I can think of? The simplest case I want to solve first before I move, let's say, to higher order polynomials. Linear. So I want a solution that is going to be linear. And so my enrichment function for the smooth part is going to be what? What is the enrichment function that I'm going to use for the linear part? So if I look back at this equation here, and I say, well, those are the enrichment functions that I'm going to use to represent the smooth part, right? And I want in the end a solution that is going to be linear. So what enrichment function I choose from that list? 1. Exactly. So that is the first one. Yeah. So I'm going to say that my enrichment function is basically going to be only one enrichment function and it's equal to 1. Yeah. And then for the non-smooth part, and this is what the rest of this lecture is going to focus on, I'm also going to choose one enrichment function that hopefully is going to behave also linearly. And I'm going to call this L alpha gamma of x. And I'm going to call it like that because there are many options I can take. Okay? And so for this very simple example, my final approximation is going to look like this. It is really not much of an HP extension anymore because I decided to remain linear. But let's keep that notation so far, and it's going to look like this. Phi alpha x plus sum alpha equals 1 to 4 u hat phi alpha L alpha gamma of x. And of course I forgot to also state the dependency of this guy in x, right? And this is a degree of freedom vector. And if you look at what we have here, let me just move it a little bit. This representation of our field is very much what we saw in the first lesson, and that I told you that if you remember the structure of that approximation, this is basically all you need to know for this course, right? And you see it here again. So our finite element space in that element contains two parts. If you take a look at the first term, this is the yeah, it is smooth, but it's also what? The first term that you see here, what is it? It's linear. It's the GFEM. It's the standard part of the approximation. Right? And the second term is the one that contains the enrichment with the appropriate behavior that we're trying to reproduce. Yeah? So again, going back to what we discussed before we started, everything we do in this class is to extend our standard basis functions, right? The standard part of the finite element space, we augment that with enrichment functions. And then you can see it here for this particular problem with a material interface. This first term that you see here, this is the standard part or standard FEM component. And this whole thing is my enriched or also extended. So if you see, if you heard about extended FEM, it's exactly the same thing as generalized FEM. This is the enriched or extended component, right? And if we look at the DOFs, well, this is my standard DOFs, and this is my enriched DOFs. And again, talking about notation, remember that the product of these two is what we decided to call the generalized enrichment function. But for now, I keep it like this. So now let's really, too much preamble, let's now focus in the real issue here, which is how do we represent those enrichment functions to reproduce the kinematics of a discontinuity. So there are many different options that you can choose. Yeah, so we're now talking in how we can write that function. Well, the first function that has been proposed was due to Sukumar and co-workers. This happened in a paper in Computer Methods in Applied Mechanics and Engineers, I believe CMAME, in 2001. And the idea is basically to use the distance function to the material interface to build the enrichment. That is the main idea behind this. So if you, let's say you take your, now this is a different, how do we call this? Because I don't want to use phi, we use that symbol already. Let's call it delta, okay? This is, say it's my distance function. Delta of x is equal to x minus x min, and then I'm going to multiply that by the sine of x minus x min dotted with the normal, where this delta x, and we're going to explain a bit what I'm writing, is just the signed distance function and then this n mean is the normal vector to the discontinuity located at x mean, which is actually the point along the discontinuity that is basically the orthogonal projection from that point x to the discontinuity. So it's a distance. So you're at a point, let's say at your Gauss points where you need to evaluate the enrichment. Well, you would compute the distance to the discontinuity, and of course it's not any distance, so it's basically the closest distance. So that is going to define a point, that this is what we define as x min. Okay, I'm going to show you in the plot in a minute. Orthogonal projection of x on gamma. So let's see how that looks like. So if we look at our problem, and well, I want to say I am evaluating, let's say I am evaluating, this is my Gauss point right there. So what you want to do is to compute that distance, right, to the discontinuity, and then I'm going to have a point right here that I'm going to call x min. Yeah, and of course that discontinuity is endowed with a normal vector, and so if you take a look at what I'm doing here, this is just x minus x min is just a vector from that point x min to the point x that I have in question. It's just a vector. So if I take the magnitude of that vector is just, you know, a length, right? It's basically just, this is just the distance to, between the point x and the discontinuity. And then I multiply that with the sign. And why do I want the sign? Well, because I want to really differentiate points that are on one side of the discontinuity from those that are on the other side. For some cases, I am interested in knowing whether a point lies on the positive side of the discontinuity or on the negative side of the discontinuity. And that sign is basically determined by this product, right? So if you take a look at back, and now I want to say, well, my normal, let's say my normal vector looks like this. This is the normal to the discontinuity, right? And now I take the dot product between the normal and that vector x minus x min. Well, clearly, if both vectors are pointing in the same direction, the sign of that dot product is going to be positive. And if they are pointing in different directions, the sign is going to be negative. And this is the way I give, let's say I give this computation a means to determine whether one point lies on one side of the discontinuity or on the other side. Yeah, everybody with me here? I can explain again if necessary. Yeah, okay. So, what this complicated expression is computing is a sign distance, right? Clearly, the first term is just a magnitude, so there is no way I can determine the sign there. And so I am multiplying that with a second term that is just telling you whether one point is on one side of the discontinuity or on the other side. And how do we do that? Well, we use the normal vector to the discontinuity, right? So I do the dot product between that normal vector and x minus x min. So you see that if the normal is pointing in the same direction as this vector x minus x min, basically the dot product is going to be positive, right? That means that the point is located in the side of the discontinuity where we have the normal vector pointing, okay?
Can you repeat that one more time?
Sure. So let's go back maybe to the figure, right? and I am interested in this point. This is x. So let me mark it x. And what we want is to see whether that point lies to the left or to the right of the discontinuity. Okay? Now, if you look at that red arrow, this is a vector that is defined as x minus x min. Okay? If this point here is my x min and this point here is my x, well, this vector that I just draw here is x minus x min. Okay? Now, if I take the dot product between this vector and the normal, my normal, remember my normal it's here. This is my normal vector. If both point in opposite directions, the dot product is negative. If they point in the same direction, the dot product is positive. So if I just take the sign of that dot product, I can already determine whether x lies to the left or to the right. Of course, to do this, you have to be consistent, and the normal throughout the discontinuity has to point in the same direction. Right? It doesn't make sense that in this element is pointing to the right and the contiguous element is pointing to the left, because all of this computation doesn't make sense anymore. You understand? But that is basically what it is. So if we look again at the expression that I use to compute the sign distance, well, this first term here, x minus x min, is just a vector that is pointing from x min to x. So if I take the magnitude of that vector, it's just a number, that's the length, the distance. And then I multiply that by the sign that I obtain by doing this dot product. That's all it is. I mean, it's really, it looks complicated, but it is really not that complicated. Okay?
If you make that normal vector a unit vector, then the dot product is sufficient for that distance.
Which vector, unit vector?
The normal vector.
The normal vector is a unit vector.
Yeah, then the part in the sign.
This part?
Yeah.
Yeah.
This part has the magnitude and the.
Yeah.
Yeah.
But we're also only interested in the sign of this. Huh? Yeah. So this sign function, this sign function, what it does is that if you pass let's say you pass a number to this function, a real value, it's going to look, if the real value that you pass is greater than 0, it's going to return 1.
Yeah. One means if you put a sign to this, then you just eliminate the magnitude of this vector, right? Because it's a dot product, then it's like there's a magnitude, then you multiply by magnitude.
Yeah, that's the way they defined it.
But if you just remove that sign and remove the magnitude, that's the same.
It is. But that is the way they define it in the paper. If you look at the paper, then maybe they wanted to make it more complicated. But you're right. Yeah, because the n vector is a normal vector.
What's the point of it?
That's the way they defined it. Yeah? So what you're saying is basically why doing this.
I think it makes it more explicit that they wrote it like this, right? Because, yeah.
I mean, it's, I don't know, when you write the paper, you try to make something sometimes complicated easier to the reader, and sometimes you try to do the opposite, right? Here, when I see this, it's crystal clear to me that, the first thing is just the magnitude. And if I want to use the magnitude explicitly in the equation, then of course I have to add the sign to it, right? And that's the way they did it. But yeah, indeed, I mean, there are many ways you could write the same thing, right? Why maybe n vector in the paper is not a unit vector, I don't know, right? Maybe. In which case, this whole discussion, yeah, this is the actual way to represent. I don't know. But that's the way they propose. But let's go now to the enrichment function, because now we have basically the means to determine sign distance. So what is the enrichment function that we're going to use? So if we look at this problem from a 1D, and I have to hurry because we have 10 minutes. So from a 1D perspective, say this is my node alpha and this is my node beta. And then let's say that that function that we just this is that function, yeah? This is my function delta of x. Well, one thing that you could do is basically to try to do this. Yeah, this we're going to call 1a. So if we are taking the absolute value of that sign distance function, right, which is basically going back to this equation and say, well, let's just get rid of that term, right? I'm just taking the absolute value. I have a function that has a kink built in. Yeah. Another thing we could do is, well, this function is really not so nice in blending elements for the reasons I described earlier. So then let's try to smoothen the behavior in these elements. So another option is to say, well, at those nodes, and I'm going to make this node beta a bit closer. I want to remain constant in the blending elements. And this may be able to help. So let's say this we're going to call 1b. And so for my simple 1D problem, the 1a, my enrichment function L alpha gamma of x is just going to be the absolute value of my delta of x. And then you can see indeed that this is actually not equal to 0 at the location gamma, right? But as I said, this function has problems in blending elements. 1b is similar. We do some smoothing. That means that our function is constant in those elements. So, by the way, this function, delta, sometimes is referred to as the level set function. So if you ever heard level set, it's just the distance or the sign distance from a point to the discontinuity. And sometimes you can actually represent this using your underlying finite element discretization. So you can discretize, if you will, the level set function, which is also called the level set function. Well, it can be represented, and I'm going to call H to associate that function again to a finite element discretization. I'm going to be able to do the same. So I have my phi alpha of x. This is my partition of unity shape functions. And now I'm going to multiply by some, let's call it big delta at x alpha. So that is actually the level set function at the node, at the mesh node. And I'm just using the finite element partition of unity, right, of my background discretization to do the interpolation. Yeah? So you see now I have a discretized level set function. It's not exact anymore, but I just compute at some points, my points in the mesh, and I'm using the finite element shape functions to provide interpolation of values. Okay? Now, these functions are really not so nice. And part of the problem that you have to solve in the first exercise of the project is to really see how these functions look like. So this is part of tasks. You will see that the Zuckerman enrichment function has some issues in blending elements, so your convergence rate is not going to be optimal, right? There was another function, and I have 5 minutes left, so I have to hurry. But the second enrichment function that was proposed for weak discontinuities is due to Moss, Nicola Moss, and co-workers coming from the same group in Northwestern University. This is where the whole XFEM name came from. It was also a paper in 2003 in CMAME. And the function looks like this. Sum, and then I'm going to use another terminology here, delta Okay. It looks like this. It looks quite complicated, right? So you see that we're using, let's see what are the ingredients of this function. We have our partition of unity. So we're basically, again, summing over all the nodes in the mesh, where these guys here are the shake functions. They show up also here. And then we have those level set values computed at the nodes. So again, you see that we're using the discretized version of our level set function. This actually is a very, very smart function. I don't know how they came up with this, but it's actually brilliant. So if I look, let's call this guy. Let's call this A. Let's use another color here. And this call this B. And now let's see how they look like. And with this, we're going to finish the class for today. Yeah. And then I want to do this is not going to work. You will see in a minute why I do that. Yeah, now I want to basically say that this guy here is my discontinuity, this is gamma. Okay? And these are just different values that I obtain. This is that function that you see here. So you see I'm taking the absolute value of the distance to that node, and I'm using the partition of unity to interpolate within. So that is the first term. It looks like that. Now if I take a look at the second term, so let me just copy this. Okay.
Are those blue dots guys points or nodes?
Nodes. And now we have something that looks like this. This is our second term. Yeah? So if you look at these two terms, and basically you take the green one, right? So you take the first one and then you subtract the second one, what you actually get is a very interesting function. Oh, there. That looks like that. Yeah? So you see the function has also a kink built in. It's a very nice function actually, because you can see immediately that the function is completely zero, totally zero in blending elements. Okay? Now, it has also a nice property that when the function, that discontinuity right now is at the center, but as the function, as you are moving the discontinuity closer to the nodes, right, that function actually gets increasingly smaller. So its impact in the formulation is less and less and less. And actually, this is one of the main issues of GFEM. The issue of discontinuities with GFEM or XFEM is that when you are moving your interfaces close to the nodes, the condition is an issue. The condition number of your global stiffness matrix is an issue. So there is actually a lot of research going on right now trying to find what they call stable generalized finite element methods, or SGFEM, which actually try to come up with nice enrichment functions that you can use in the generalized finite element framework so that your system of equations always remains well conditioned. This is an issue. So as I said, just to finish this lecture on weak discontinuities, as let's say delta is going to 0, so your distance to the nodes, let's just write it down. Distance to the nodes tends to 0, yeah? The function also decreases. Yeah, just to complete. So it has a nice behavior for. There is some people waiting. Okay, okay. Let me just very quickly state to finish that well, the convergence in terms of convergence rates. Just to finish, we have in FEM 0.58 roughly. This is what I have here. For GFEM, this is if you don't do anything, in particular if you don't add any enrichment. For Sukumar, you get with smoothing, you get 0.7. And then with MOS, you recover an optimal rate of convergence of 1. Okay? Nice. We are done with the GFEM for weak discontinuities. In the next class, what we're going to look at is the implementation details of this. And we're going to look also at how you can test your program, right? So how you build finite element software from the beginning so that you can add complexity, and you keep testing small units. It's like you prepare building blocks so that you can increase in complexity. Okay, how do you check stuff in your finite element software? So the next class is going to be very useful for you guys. Thank you very much, and we address the questions that you have outside. Okay.